Yeah. So in the early, well, in the TCGA project, after the scientists profiled many different tumors, usually the consortium will get together to decide how many subtypes do we have. In each major tumor types, they have to decide how many subtypes, right? Do we go with, you can imagine this is like a K-means clustering. Do we go with K equals to 3 or 5 or 25, right? So the question is, do we see a significant difference in the mutations or the expression or the treatment decisions? I think the most important thing is whether the patient will have a different survival and whether they should be treated with something different. And that will determine how they decide how many subtypes. And so looking at that, understanding the survival of the patient in each subtype would be very, very important. And so for that, we'll have a very, very short survival analysis. By the way, survival analysis can be a whole semester course. We're just giving you like a 10 minutes quick overview of survival analysis. And for example, you can use survival analysis to answer a number of interesting questions, such as, do patients receiving a particular type of treatment live longer? Or you can ask, are smokers more likely to have cancer recurrence or, cancer not recurrence, like a cancer incidence? So patients with this particular subtype, are they more likely to metastasize, right? And so for that, anytime you deal with real patients in the survival analysis, there's a very realistic thing called censored data. The value of the measurement or observation could be only partially known. For example, some patient has left the study, or the study has concluded the patient hasn't died, but doesn't mean that he will not die after the study finished. And somebody, for example, we do also see cases where you call the family and they don't answer the phone anymore. They kind of, when they leave the study, it could be because of a few things. They can't tolerate the drug anymore, or they are just too sick, or they don't want to do it. They're like, okay, they just say, oh, I found an alternative medicine. They talk to a shaman or whatever. So it's many reasons when people could just leave the study. And so, for example, we are showing day here, but in a real clinical study, this could be months, could be weeks, right? So initially, you might have 4 people under study, and then usually in these studies, you have a time interval, right? You look at every week or every day or every year, and you ask, okay, so say at this second day, 1 patient died, you still have 4 patients in here, right? So the probability of death is 25%. The probability of survival is 75%. But then, say in the 3rd day, no patients died, but then 1 patient that just they either moved away or they decided they don't want to get this treatment or whatever, you just can't follow them anymore. And so you don't observe anything yet. And then the next one, you can see here, it's this patient died. And that's basically 2 patients, 1 died. That's a 50% death rate. But if you look at your total, like the survival, it's kind of at this 75% divided by half, right? Because 1 patient kind of left here halfway. And then at the last point, there's say another patient who left the study. And this, if they leave the study, we don't know. We just assume that they're still alive, right? So there's still 38% survival. And so you can see if you have a real study like this, so this is your total number of patients that are still in the study. This is, say, either days or weeks in the study. And this is the event. This event could be a death event, right? So in 0 day, you have 21 patients going into the trial. In the first time point, 2 patients died. And you can calculate, 19 divided by 21, this is 90%. But yeah, so here is, if you don't consider anybody if you consider, you don't worry about the sensor data, you can see here basically, then 2 people died, then it's 81%, and then you have 17 people left, 1 person died, and so you can calculate basically this survival probability. You know, it's the number of patients that passed a certain time point, and then divided by your total patient in the very beginning, right? The reality is that a lot of times, in addition to the people who potentially, you know, died, there are also other patients who, for some reason, just left the study because they, you know, you just can't keep track of them anymore. And so in survival, if we consider censored data, in this case, initially, yes, we did have 21 patients. At this time point, we know that 3 patients died. And so you can calculate the probability of the survival in here. But then in the next point, you don't have 18 patients left because 1 guy is gone. Somehow they dropped this from the study. And so the denominator is no longer 18, it's only 17. It's the available number of patients who are continuing on with the study. And then 1 died, and so the survival probability is actually 0.86, not 16 divided by 18, right? And then say another patient left. So you can see here the difference is that the denominator is always just the number of patients who are still left in the study. And that's kind of important. When you calculate this final survival curve, what you are showing is the this probability over time, you know, and you can compare it with 2 groups. For example, if somebody goes through 1 treatment versus the other treatment, there you can't have people leaving the study. So in this case, every time you have a drop, you know, this probability go down, is because there is a patient who, for example, either their tumor relapsed or the patient died. It depends on what you are really looking at as the event. But anytime you see this little tick in here, you see here the little bar, that means a patient left the study. You just don't have information for that patient anymore. And so those are, you know, just the natural events which happens in a lot of these clinical studies. But when you calculate the patients, you only use the available number of patients to calculate the probability at each time point. And so this is a very standard Kaplan-Meier curve. And so you are comparing the 2 groups and you're asking, are they significantly different? If you don't know the statistics, you can just, you know, see you want these 2 curves to be as different as possible. If they are really far apart, you have a very significant p-value. So KM curve, easy to read, right? But if you want to see how some of the probabilities are calculated for survival, there are 2 types of tests you could do. One is a log rank test. So you can see here, each row here is an event, either it's like a day or week, you know, the time point that you are looking at. And then, let's see. This is the number of failures. Failure means either the patient died, or in this case, or it could be relapse, or you know, whatever event you want to capture. And this is the how many patients are still in the set in the 2 groups, right? So, but then, so you can imagine. Let's see. You are trying to compare the 2 groups, and you are asking how many events. So initially, you have 2 groups, each have 21 patients, and then at the first time point, let's just say 2 people died in this group. And then the second day, 2 people died again in this group. The third day, another 2 people died in this group, right? So you can see in this situation, it's probably more events happening to the second group. As the first group, you know, occasionally there are patients dying, but it seems like a lot more patients are dying from the second group. We are trying to ask whether those type of death events or whatever the events, failure events happens evenly in the two groups, or they're happening more towards one group from the other, right? And so at every point, you are calculating the expected number of events. For example, because we know there are 2 patients died, so out of the 42 patients, because this group only have half of those patients, you are expecting the death events to also be evenly split, right? So there are 2 total deaths, and because this group have only 21 patients, you expect to have half of it. That's your expected. But the observed is that there is nothing in this group. The observed for here is the 2 patients all coming from one group, right? And then you look at the next group. Again, there are 2 death events, and you're calculating how many total patients are still available and how many are from that first group. And so you can see here, in this calculation, the denominator here are what are the total number of patients that are still available at this time point, and also how many patients are available in my group. You know, this group is 12 out of 18. This is 6 out of 18. So it's already censored data. What are the available data you are using to calculate this? And so because at every time point you can calculate the observed versus the expected, right? So this is asking what is your observed over expected, and every time point you can calculate this. At the end, you're asking, is the observed versus expected significantly different? And so for the log rank test, what we are expecting is called proportion in the risk set. You are hoping that the risk should be occurring with the null hypothesis, is that the risk for this failure event, whether it's death or recurrence or whatever, is proportional to the sample size that's available at that time point between the 2 groups. And you're asking how different are they, right? Then you can just use chi-square test to see whether you observed versus expected is significantly different or not. And so normally with log rank text, you are considering 2 groups and checking you know, whether a treatment is making a difference, or whether patients say whether if they have lung cancer, whether the smokers and non-smokers have different survival, or whether they respond to the drugs better or worse. But sometimes you can also have more variables. You could look at, for example, expression of some genes, or you want to say, in addition to, so for example, we could consider one variable as patient age. You are wondering whether the patient age make a difference. You are wondering at the time of diagnosis, whether the tumor stage make a difference. You are wondering whether the gender makes a difference, whether smoking makes a difference, right? And those variables can also be both discrete, which means it's potentially categorical, or it could be continuous, which is like, say, gene expression value. And so when you have so many different things, you could use a Cox regression to ask, you know, if we look at all of these together, can you see a difference between the different groups? So we have a question. Yes, Jack.
Yeah, sorry, can you go back to the log rank test? Here, like can you explain like how to exactly calculate this statistic at the bottom? Like, I'm not sure like how to do the variance.
How do you, so normally how do you do chi-square test in a 2x2 table, right? You always have, you have many observations, and you have many expected, because every row is a value.
Yeah,
right?
I'm just kind of lost on like for example, use this example, like what kind of number are we plugging in to the formula?
So every row you have expected and observed. Every row you have expected and observed.
Uh-huh.
And you can look at the variance of those, right?
Yeah, it's just like can't really remember what kind of formula we should use. Yeah, but
Yeah, maybe as I mentioned that so in general you could look at this in a survival course. I think you can see this explained very clearly.
yeah. Oh, okay, sure.
Yeah, so basically log rank tests just give you one variable at a time. You ask whether something give you a difference. Whereas the Cox regression, they give you many different variables. You can estimate them together, and it can help you estimate a coefficient to try to separate the groups. And it can actually try to help you separate things to see whether some variable can make a big difference. And it can also tell you whether a particular variable is significant or not. For example, if you include many variables in here, if some coefficient is close to 0, you will know that, okay, that variable doesn't really matter at all. But say patient stage is important. If it's stage 1, the patient do better. If it's stage 4, the patient do much worse. You will have a survival result where the coefficient will be quite statistically significant. So when you do this Cox regression model, it will tell you that this variable is significant, the next variable is not so significant. And so you can look at many variables together, and they could be either categorical or continuous, like gene expression levels. Yeah, so that's kind of the different ways you can look at this. Yeah, so let's see. This one is using 2 groups of genes. So supposedly you have, say, the PAM50 gene expression, right? You can look at 50 genes, and using the Cox regression model, it will help you weigh the patient. So, and then see, looking at the survival, say, this gene really has this effect on survival. That gene has this effect on the survival. And so based on the expression of all the genes, it can help you separate the patient into the low risk versus high risk groups, which can be also very useful. So that's how, you know, if you have the differential gene expression from the different groups, you can use that in your Cox regression to see whether the subtypes have different survival, and you know how those genes are associated. By the way, none of these are causal. They are just associations. They don't tell you what this gene is the reason why the patient had better survival. It just says if the expression of these genes are overall like higher, or you know, based on whatever weighting is higher, the patient will have better survival.
Do the ticks still indicate a patient has dropped out?
Yeah. Yes, okay. Exactly. That's the sensor data.
Okay, so it just seems like, I don't know, it seems kind of weird that there's a lot of patients that dropped out in the low risk signature. Is that typical, or yeah?
It depends on the study, I would say, and also depends on what you mean by the event. It could be a death, it could be a recurrence, it could be whatever reason. Yeah, so it depends on what you're looking for. I don't think it's always the case like this.
I have a question.
Yes.
So how do you derive hazard ratio from the Cox regression?
That I think will probably take a whole course to do. I think you will take a lot longer than this lecture. We can include some videos for, you know, like we can find these similar videos online. Maybe also with Jack, we can find similar videos to show you how to do the log rank test as well.
Yeah. I just figured.
I'll include those videos in
if you don't mind, I can answer that, how to calculate hazard ratio. It's just the exponentiate of the beta coefficient you estimate, and you get a hazard ratio for 1 unit increase in that variable.
Okay, thank you, Jack.